So the first talk is a deductive verification infrastructure for probabilistic programming. And we have Philipp Schröer from RWTH Aachen presenting the work. Thanks.
Yeah, thank you. So I'm Philipp, and I'm going to talk about our new verification infrastructure to verify probabilistic programs. This is joint work with Kevin Batz, Benjamin Kaminski, Joost-Pieter Katoen, and Christoph Matheja. So let's start with a simple probabilistic program. This is what we call the geometric loop program. We have two variables, C and run, and we initialize those to 0 and true respectively. Then we have a loop, and it runs while run is set to true. And now the loop body has this probabilistic choice, right? And with probability 50%, we enter the left branch, and we basically terminate the loop by setting run to false. And otherwise, with the other 50%, we increase the counter C by 1. So this is a simple probabilistic program, and we can look at various interesting properties about this one. So, for example, we can look at what is the probability of terminating in a state that satisfies C equal to 2. This is 25%. Then there's another property, the expected value of, so for example, the counter C after termination. So there are infinitely many possibilities, but the expected value is 1. And then this program is also almost surely terminating. So this is something about the probability of termination. There is a run that runs forever, right? There is this run where you always increase the counter, but the probability of it is 0. And then further, this program is what we call positively almost surely terminating. So this program has a finite runtime, which means in this case, the loop guard is evaluated twice, so the expected runtime is 2. And so we want to look at programs like these and obviously more complex ones and properties like these and verify them. So in general, we are interested in lower and upper bounds on expected values of probabilistic programs, expected runtimes, almost sure termination, positive almost sure termination, amortized expected runtimes, and then even more, probabilistic sensitivity, conditional expected values. And then in this other box here, I put in some of our proof rules that we use. So Park induction, K induction, martingale-based reasoning is required to reason about loops in probabilistic programs, so we also want to use them. And the motivation for our work really is the following. How do we automate the verification of probabilistic programs using these different properties, these different proof rules? And crucially, how do we make this extensible? How can we design it so that we can add more properties, more proof rules without lots of engineering? And the idea is inspired or taken from classical deductive verifiers, where this was very successful. You might know Boogie or Viper. These are intermediate languages to encode verification problems. And what we are doing is build an intermediate language to encode verification problems for probabilistic programs. Okay, so we want to build the probabilistic version of Boogie or Viper. So what does this look like? Well, we present our new intermediate language that we call HeyVL to verify probabilistic programs. And then in addition to this, we have a new logic, an assertion language to reason about quantities such as expected values, and we call this one Halo. And the semantics of HeyVL are given by so-called verification conditions, so that's this VC generator there. And tell us whether a program verifies or not. Then we have encodings of all of these different properties and proof rules into HeyVL that we also describe in our paper. And then finally, we have an implementation that takes a HeyVL program, generates these verification conditions in this logic, Halo, and then uses an SMT solver to try to determine whether the program verifies or not. And finally, we also implemented a front end, which makes this easier which automates the encoding of those proof rules and those properties into HeyVL itself. So this is our paper and our contribution in one slide, our verification infrastructure. So let's see how this works. And let's first talk about classical specifications for probabilistic programs, for classical programs, sorry. So in the classical setting, we look at predicates. Predicate is an assignment that maps each program state to a Boolean, yes or no. And this whole triple here for total correctness says, okay, if we start in a state that satisfies P, then we terminate, and also we terminate in a state that satisfies Q. We can phrase this somewhat differently and say P represents a subset of the states terminating in Q. And in deductive semantics, using what's known as weakest preconditions, we can say, okay, P is a subset of the so-called weakest preconditions of Q, which represents exactly the above here. Now, what's cool about intermediate verification languages is, at least that's one thing, you can use assumptions and assertions, so verification-specific statements to encode this specification here. You can assume the precondition before the program, and you can assert it at the end. So this creates this proof obligation, and then we encode the program as in the language again, for example, with proof rules for loops. And this is something that we want to do for probabilistic programs as well. So what's the setting in probabilistic programs? We look at now random variables or expectations, not just predicates. And these expectations, f and g, are mappings from states to non-negative real values or infinity. And now this triple here that I put down says for every initial state, f is a lower bound to the expected value of g. Okay, so now we shift to lower bounds on expected values from subsets. In deductive terms, this is there's a thing called weakest pre-expectations, which generalizes weakest preconditions. So now we say f is a lower bound to the weakest pre-expectation of g. And in Javier, our intermediate language, you can write this specification in the same way. You can assume the pre-expectation now f, and then you assert the post-expectation g, and you encode the program again. Now notice that f and g evaluate two numbers, right? So f might be 42 in some state or 3, and not just true or false. So now the crucial question is, how does this work? What does assume and assert mean in this quantitative setting? What is the semantics of Javier? And to understand this, we look at the logic on expectations, logical reasoning about these values. For the assertion, we assert an expectation f with a post-expectation g. We define the semantics as a minimum. So we take the least numeric value in each state. This corresponds to the classical setting where you would say both f and g must be true. And here, this is the minimum. But a bit more interesting or a bit more complex is how do we understand a quantitative assumption? What does assume f mean when f can evaluate to a number, right? And for this, we want to find some kind of implication on expectations. F and g are expectations, and this must evaluate to numbers again. And to understand what such an implication should look like, what it should be, we look at some properties that we want to have for it, right? And one property is that an implication, when we introduce it, g implies h down here, must make a proof easier. What I mean by this, g implies h, and with the lower bound f should be the same as looking at the minimum of f and g as a lower bound to h. Okay, so this means introducing an implication on the right-hand side of this inequality is the same as shifting this implication or this assumption g to the left-hand side, which really makes this inequality easier. Okay, so here the meaning is implications make verification easier. And this gives us what's known as a hating algebra, which is where the names Halo and Javier come from. The second property that we want to have is this deduction theorem that gives us exact comparisons, so to say. We compare two expectations f and g, and f is a lower bound to g if and only if our new implication that we're looking for evaluates to infinity between these two expectations. Okay, so we have on the left-hand side the property that tells us implications make stuff easier, and on the right-hand side it says we can exactly using implications encode comparisons, and these are very important to encode proof rules, for example, for loops. So what does the implication now look like? This is an example. 42 implies g. So g here is on the x-axis, and the interpretation of 42 implies g of this quantitative implication is assume g at least 42 to be true. What do I mean by this? Formally, this means in every state you check, is 42 a lower bound to g, and that's the top right line over there. And then we give the quantitative equivalent of true, so that's infinity. If 42 is not a lower bound to g, then we return g unchanged. Okay, so this really means if g is at least 42, then we pull it up to infinity, otherwise we don't do anything. And so this is our basis for the logic of on expectations. We have an assertion and an assumption on expectations. So let's look at a very simple example. This is a very simple behavioral program with a quantitative assumption, C plus 0.5, and then a very simple probabilistic choice, and then the assert C at the end. And we want to check whether this program verifies in behavior. What does it mean in this intermediate language, intermediate verification language to verify? It means that we need to evaluate the semantics of this program, and we start at the bottom with infinity. We evaluate the semantics, and we must obtain infinity again. Then we say this program verifies. This is how we encode all of our proof rules. So we start at the bottom with infinity. We apply the semantics of the assert that we've seen before. That's a minimum between infinity and C, but this is the same as C. So we can simplify. And then we do the probabilistic choice, and the semantics is the expected value of C, which turns out to be 0.5 times C plus 0.5 times C plus 1. Okay, so with probability 50%, C is not changed, and with probability 50%, it decreases by 1. We can simplify this, we get C plus 0.5. And this gives us the implication C plus 0.5 implies C plus 0.5, which means this program verifies. And this encoding tells us, okay, C plus 0.5 is indeed a lower bound to the expected value of C. So this is how we encode simple specification for lower bounds in behavior. And so we've seen this third statement as a minimum, we've seen the assumption as an implication, and the Havoc statement is a new one. This is a non-deterministic choice that corresponds to an infimum over all possible values of the variable x. And this kind of design satisfies one of our main goals, namely that behavioral generalizes classical IVLs. So in the classical IVL, we have a Boolean AND. We have a minimum. In the classical IVL, we have an implication. We have the Gödel implication. In the classical IVL, we have a for all, for the Havoc semantics, and we have an infimum. So really, in a formal sense, we generalize classical IVLs to expectation-based reasoning. Another goal of ours was to reason about upper bounds on expected values. This is very natural when reasoning about expectations of probabilistic programs. For example, you want to say the probability of crashing is at most 10%, or the expected value is at most 42, right? So this is not that common in classical reasoning, but here it is. So this is why behavioral supports these co-assert, co-assume, and co-Havoc statements, which correspond to the duals. Maximum Gödel co-implication, omitting this one here, and for the co-Havoc, it's a supremum. Okay, so you can see these are exactly dual and allow us to do upper bound reasoning in our verification language as well. So to show you that this works, we have more than 40 examples verified with 12 proof rules for loops, doing lower and upper bounds reasoning, for example, with partial and total correctness, so that's probabilities, expected values, conditional expected values, expected runtimes, almost sure and positive almost sure termination. We also have encoded procedures with recursion, and user-defined data structures are also supported. And the point of this slide is to say, if you find a new proof rule, you can also encode it into AVL and basically get automation for free. That's the hope. So just briefly to show you how this works for a very simple proof rule, let's say in the you have a loop while b do s, and we use a rule that requires invariance. In the classical setting, in the classical encoding, what you can do is use this encoding of a specific proof rule. This is the whole logic proof rule. In the beginning of the loop, when we encode it, we need to ensure that the invariant holds before the loop. Then we enter the loop, we assume that the invariant holds, and at the end we assert it again. So that's kind of the intuition. In the probabilistic setting, we now have an invariant that's quantitative. It's an expectation. So it looks very much the same. We still assert the invariant, assume it, and assert it at the end. But we have differences, right? We have an assume 0 instead of false. That's the quantitative version of it. And we also have this additional validate statement that it's necessary for the correctness in the probabilistic setting, and we have details on this in the paper. How do you get started with behavior? In the paper, we provide the details on syntax and semantics of behavior, our intermediate language. We detail our assertion language to reason about quantities, and we have case studies described for these different encodings of these proof rules. Online on caesarverify.org, you can find our tool. Caesar, it's written in Rust, it's open source, and we're actively maintaining it. So you can also find the language documentation and an extended version with more details of the paper. That's it. I'm happy to take any questions.
Any questions? So I have a couple of questions. So one is, I see that you are working with expectations, right? So
Yes.
it's only the first moment, or like, can you generalize this to higher moments, like variance, or the third or fourth moment, for example?
So when I say expectations, I just mean mappings from states to values, right? And this includes higher moments, but also, let's say, an exponential or something. So this includes, yeah, like in theory, reasoning about all moments.
I see. And what kind of solver are you using for solving these verification conditions?
Right now we're using Z3, so we are encoding this halo, this verification question about halo as a Boolean query into Z3.
Got it.
But we are also looking into, trying more.
Thanks.
Hi. So in propositional reasoning, you have weakest precondition, which corresponds to the box in dynamic logic. I'm curious if your co-assume and co-assert, does that somehow correspond to like the diamond of dynamic logic?
Okay, so I'm not sure. I'm not too familiar with dynamic logic. I would be happy to talk to you about
Well,
this.
basically the idea is the box is you're sort of universally quantifying over all the non-deterministic possibilities, and the diamond is like you're existentially quantifying.
I mean, the universal and existential kind of corresponds to the Havoc main coordinate equations. But I wouldn't, I would be cautious to claim any similarity. But we can talk about this.
Sure.
This sounds interesting.
All right. Thank you so much.
Thank you.